All right, guys. Just as promised, we're gonna go and solve some sample problems and walk you through on how to solve and apply the concept under Bernoulli energy equation, mechanical energy and efficiency, and as well as conservation of mass. We'll start first on the last part, which is conservation of mass, and as a general guide. Okay, so how can you make use of this sample problem walkthrough? So have the lecture copy at your side, whether it's PDF or the pre-recorded session if you haven't grasped the lecture part. And then when watching the walkthrough, try pausing it and solve it on your own first, and then let it play out if you want to check the solution. And more importantly, I want you to have fun. And uh, and it's a lot easier to remember it that way when there's a core memory and a core emotion um, bundled together with it. Also, I took the liberty of compiling all the formulas related. And you can also check them out in this in our reference book, Sengel, Fluid Mechanics and Fundamental Applications, third edition, um, published in 2014. So you can go hand in hand, or you can print this out so that and feel free to add more formulas here if I fail to provide the other formulas here. But it's best to solve them so that you know where the derivations are. For example, for Torricelli's equation for the stagnation pressure, and the velocity when there's a stagnation pressure, and how they came to be. All right, so let's start solving. All right, so let's start with some few sample problems. Um, let's start with this one, a sample for conservation of mass. So say we have this particular inlet and outlet here, and this is the control volume region. It has one inlet and two outlet, where point 1 has a diameter of zero point 0.1 meters, with an unknown velocity 1. Point 2 has a diameter of 0.07 meters and velocity of 2 meters per second, and at point 3 has a diameter of 0.03 meters and a velocity of 1 meters per second. We're here to find the velocity at point 1, and we assume that the fluid is incompressible. Okay, so how do we go about this? Hmm. We can take it step by step muna, no? So you can always rewrite this lang, just to be sure. So we're here to find velocity 1. So we know that's gonna be meters per second. So our solution here, if you would recall, the conservation of mass, it's gonna be, so there's multiple exit points and one end point here. So all we have to do muna dito is try to get the summation of mass flow rate in equals to mass flow rate out. Since this is incompressible, we can further expand our solution here into this. So basically, this is mass flow rate at 1 equals to mass flow rate at 2 mass flow rate at 3. And we can expand further. Recall that mass flow rate is simply equal to also density times fluid velocity and times the area. And substituting that here, we will have density 1, velocity 1, and area 1 is equals to um, density 2, velocity 2, and then area 2 plus density 3, velocity 3, and area 3. However, since it doesn't say anything about the fluid, but we can assume that the fluids here are of the same property. So meaning they have the same density and only different velocities in area. So we can actually eliminate the density here, since all of these are gonna be the same anyway. We are left now with um, the product of the velocity fluid and its area. In this case, velocity 1 times area 1 here, which were given. Okay, we can expand that further by getting the area here. So this is a circular tube here. So the area, we need to get the area here. So it's gonna be V1 meters per second and times pi over 4 d1 squared. That's in this case meter squared. Is equals to, since pi over 4 will be a common thing here, so let's just put it here. So area of the circle will be pi over 4 d squared. So we can extract pi over 4 here and have it do it this way. So v2 d2 squared plus v3 and then d3 squared. Okay, and then again this one we can cancel out pi over 4, so let's cancel this, and now we can rearrange the equation and just isolate v1 since that is our unknown. And the equation would look something like this. So v1 is equals to v2 v2 d2 squared plus v3 d3 squared, and then divided by d1 squared. And so we just substitute the known values around here. 0.2 we have v2 here, so it's gonna be 2 meters. This is gonna be 2 meters per second. 2 meters per second, and then times 0.07 squared, so that's going to be meters squared, plus v3, which is 1 meter, so that's going to be 1 meters per second, and then times 0.03 squared divided by our d1 squared, which is 0.1, so it's going to be 0.1 squared meters squared. Okay. Wait lang. Let's just break that apart. Okay. All right. Here. And then from there we can cancel out units. So obviously the n unit here will be meters per second. So meters squared, this will be combined later. So it's going to be leaving us with only meters per second. So the answer here, if you do your calculator, so that's going to be 2 meters per second times the square of 0.07 plus basically 0.03 squared divided by 0.1 squared, it will give you 1.0 meters per second. And we'll get back to our answer. Okay. Now you could always check. So you can substitute it by getting the mass flow rate at 0.1, and the mass flow rate of 0.1 should be equal to the sums of mass flow rate 2 and at 0.3. That's one way to check it out. Okay, let's have another problem naman for conservation of mass. So here we have sample problem number 2. It is a garden hose problem. So this is a water flow through a garden hose nozzle. A garden hose is attached with a nozzle and is used to fill a 10-gallon bucket. The inner diameter of the hose is 2 centimeters, and it reduces to 0.8 centimeters at the nozzle. Oh, okay. So it takes about 50 seconds to fill the bucket with water, and we're here to determine the volume and mass flow rate of water through the hose, and B, the average velocity of water at the exits. Okay, so we make several assumptions muna dito. So we're given several values here, pero let's just put them one by one. So we're here to find the volume flow rate and the mass flow rate. So that's our A. We're also here to determine the average velocity of water at the exit. So we're gonna need V exit or V2, so to speak. And it's gonna be in meters per second. This one is gonna be in meter cube. This we're all using metric units naman, so meter cube per second, and this is gonna be kilogram per second. Okay, so let's state muna yung given natin. So first things first, we have already a volume. So volume, just gonna put it that way. So that's 10 gallons, and we have time t at 50 seconds. We have diameter 1 at 2 centimeters. Oops. And we have diameter 2 at 0.8 centimeters. Let's put it here. So the diameter 2 at 0.8 centimeters. Okay. Now we can begin solving. Okay, solution. So to get the volume flow rate and mass flow rate, we already have volume here, and there's another way of getting volume flow rate. And since we're given already a volume and a particular rate at a particular time t, so all we have to do is just convert that, and volume flow rate could be equal to the volume, that's going to be the capacity of the bucket, so that's going to be 10 gallons divided by the time t. And if it takes 50 seconds to fill the bucket with water, so that's technically the overall time. And so from 0 to 50 basically, so you could put that as delta t. That's 50 seconds, so let's put that as delta t here. So v here is technically 10 gallons over 50 seconds. Let's just convert gallons into to liters, so that's gonna be times 1 gallon is about 3.7854 liters. Let's just write that properly. So liters. So this one's gonna cancel out. Wait. Okay, this one's gonna cancel out. Cancel, and then that would equal to around 0.757 liters per second. Okay, so that's our volume flow rate. For mass flow rate, if you recall your formula, could be density times area times velocity. We could also do that, and but we don't have velocity inlet, so but we can make use of volume flow rate already, which is density times volume flow rate, which is equivalent to, since we're talking about you can convert this to meter cube, but you can also convert it to 1 kilogram per liter, that's for sure, or 1,000, 1,000 per meter cube. Density, this is assumed to be water, so it's gonna be 1 kilogram per liter multiplied by 0.757 liters per second. So canceling out liters here, leaving us with kilogram second. And the final answer is gonna be around 0.757 kilogram per second. Okay. So that is for our A. Now, so this one's the solution for A. Now for B, we're here to ask for the exit velocity. It's a good thing that we know the cross-sectional area for the exit, which is d2, 0.8 centimeters, and the area, since this is a post, so it's going to be circular, so that's the area of the exit, is equals going to be pi over 4 d squared, or we could also simply just write pi r squared. It's the same thing. And that's gonna be pi times 0.8 centimeters, so that's gonna be 0.8 divided by 2, so that's gonna be 0.4. 0.4 squared cm squared times 1 meter squared divided by 100 cm squared is equals to, let me just click my calculator. So it's gonna be pi times 0.4 squared that's gonna be 100 squared, by the way. Yep, there we go. Divided by 100 squared. Yeah, so it's gonna be 0.0000502 meters squared, or 5.027 times 10 to the negative 4th meter squared. Okay, but we are not yet done, so let me just rearrange this now. Put it here. And actually, we're gonna make it smaller now. Okay, there we go. And then we're just gonna find now the velocity at the exit, since recall that volume flow rate is also equal to velocity times area, fluid velocity and area. So we could isolate this, and since volume flow rate is gonna be equal all throughout naman, only with different area and velocity, all we have to do na lang is just isolate our velocity exit. So velocity exit is simply volume flow rate divided by area of exit. If you're wondering, since volume flow rate 1 will be equal to volume flow rate 2, since they're all the same single path hose naman, it's gonna be steady flow. Okay, so substituting it, we have here at 0.757 liters per second, which we could, just divided by the 5.0027 times 10 to the negative 4th meter squared times 1 meter cubed divided by 1,000 liters. And our final answer would be, wait, let's just do some unit analysis dito. Okay, so natin dito. And then, so liters will be cancelled out. Meter square will be equals to meter na lang dito. It will be meters per second. So we're going on the right path. So the final answer here is 1,000. And then 0.757 divided by this one. It will have 15.06 or 15.1 meters per second. Okay. Yeah, that's about it. Okay, So let's try, for example, under mechanical energy and efficiency. Here in sample problem 3, we have here a lake, and we have a turbine in the mountains. It's not exactly a high mountain, just 50 meters. And this turbine will spin and create mechanical work, which in turn, the generator provides electricity. We're provided these values, the height of 50 meters. We have a 95% generator efficiency. And then we have a mass flow rate at the outlet of the turbine at 5,000 kilograms per second. So let's try to incorporate that using the formulas we learned in the mechanical energy and efficiency. So let's leave the problem muna. The water in a lake, large lake, is to be used to generate electricity by the installation of a hydraulic turbine generator. So here we are. The elevation difference between the free surface and downstream of the dam is 50 meters. Okay, and water is to be supplied. At a rate of 5,000 kilograms per second. That's going to be our mass flow rate here. So we can assume that that's going to be the mass flow rate in and out. If the electric power generated is measured to be 1,862, okay, kilowatts, so that's kilojoules per second, and the generator efficiency is at 95%, we are here to determine the overall efficiency of the turbine and the generator, and the mechanical efficiency of the turbine, and then finally the shaft power supplied by the turbine to the generator. Okay, so let's do that step by step and writing them down. So our required here, so we're here to ask for, let's just put it here to save space. So we're here to find, and let's just put it in symbols. So the overall efficiency of the turbine generator. So we put that as efficiency of the turbine generator, and the mechanical efficiency of the turbine. So we do that by getting the so mechanical efficiency of the turbine. So that's gonna be n overall, basically. We're gonna put it as n overall. And then finally, we're here to determine the shaft power supply. So it's gonna be the shaft out. Okay, so we are also given with the following. Wait lang. Sorry. Again. Yeah, so N turbine. Here. Just turbine. Then a workshop. Okay, so we're given several things. First things first, we're given a mass flow rate of 5,000 kilograms per second. Okay, we know that the height difference here, we could, that's gonna be 50 meters. So technically that's H here. Technically that's delta H, or if we could also call it delta Z, would be 50 meters. And assume that G, it's gonna be 9.806 meters per second squared. And then I think we can solve it now. We also have a efficiency of the generator of 95%. Okay, let's start now with our solution. So for A, so for us to determine the A, we just need to establish first our total mechanical energy, or to change the mechanical energy from point 1 to point 2. So in this particular case, it's going to be total mechanical energy, E mech, is also to your E1.2 minus E1, which is also equal to your pressure at point 2 minus P1 over density plus P2 squared minus V1 squared equal divided by 2, your kinetic energy, and your J and your delta Z, which is basically Z2 minus Z1. Okay, and fortunately, we have the following. Since the fluid is coming from a higher elevation, so we definitely have potential energy here. Okay, gets. So let me just rewrite the equation here. So no wonder it's gonna be P in and P out. So it's gonna be out. So P inlet, because there is much more potential energy on the top there. Okay, so E inlet energy in minus energy out. So let me just rewrite this again. That's gonna be P in, P out, P in, V in, V out, and then this one is gonna be Z in and Z out. You'll know why later. So let's just group that together. Okay, I'm still recording, right? I am. Okay, good. Let's just group that together and then cancel out a few things. For one, when both ends are exposed to atmospheric, so meaning this will cancel out. Since we have the same mass flow rate, we can assume that the velocity is negligible too. Okay, it's gonna be 0, 0, leaving us with this one. Didn't say about our area here, but it does say that it's gonna. You can assume that's gonna have the same diameter inlet and outlet anyway, and which generate us the same velocity then, leaving us with potential energy here. And this one is simply 50 meters. So knowing the change in total mechanical energy, we can have now 2G times G times 50 meters times H in this case, or you can put Z. So here we're gonna be 9.8066 meters per second squared times 50 meters, and we're gonna convert this into the unit of the mechanical energy is gonna be on a per unit mass basis. So we're gonna have to add this one. It's 1 kilojoule per kilogram over 1,000 meters squared second squared, which is equal to, let's just group them all together, and then kilojoule so this was going to be Newton. It's going to be canceling out. Meter squared per second squared. Okay, there we go. So meter squared per second squared, it's going to cancel out definitely this one, and we will have the answer of, let me just do some calculation on my end. 9.8066 times 50 divided by 1,000. That's going to be 0.490. Yeah, I'm going to use 0.490, 0.493903 actually. This kilojoule per kilogram. kilojoule kilogram. So that's one. So let's just highlight this now. We have that already. So that's good news. What we have to do is just arrange our equation here properly. Yeah, it's taking a lot of time. There we go. So it's just gonna move it here. Okay. So actually, I think it's best that I move it here. So the next part for this particular is to now we can determine the mechanical energy that's being supplied to the turbine by the fluid and its overall efficiency. So yeah. Recall that the equation for the mechanical efficiency of turbine, the overall mechanical efficiency, is the mechanical energy of the fluid is simply, yeah, so the mechanical energy, change in mechanical energy of the fluid is simply mass flow rate times the mechanical energy in minus E mech out, which is simply, this one is already given, that's 5,000 kilogram per second, and this one we already find out, which is 0.4903 kilojoule per kilogram. So when you solve that, kilograms will cancel out and you are left with 5,000 times 0.4903. So that's about 5,000 times 0.4903. That's 2451.5. Oh, that's weird. 5,000 times 0.4903. Super round off. Yeah. Your book rounded it off way off, so I'm just gonna write a different answer lang dito. Okay, so that's gonna be 5,000 times 0.4903. That's gonna be, let's just make it 2451.5. That's gonna be kilojoule per second or kilowatts. Okay. And then from here, we can now determine now the efficiency of the turbine generator. And recall that the efficiency for turbine to the generator, let's just shortcut it, is gonna be mechanical power. It's just simply the efficiency of the it's basically the electrical output which you're given divided by the mechanical energy of the fluid absolute value. Oh, yeah. So it's gonna be a mechanical fluid. So that's gonna be equals to 1,862 kilowatts divided by 2451.5 kilowatts, and this will give you 1,862 divided by, so that's about 0.0759 or roughly 76%, or 0.760. So that's translate to 76% turbine generator efficiency. So let's just mark that up. Okay, this one. All right. So that's for A. We also need to determine the mechanical efficiency of the turbine. So luckily, we already have the efficiency of the turbine generator here, and the other formula for determining the turbine generator is turbine generator is simply the product. Wait, let me just write that down again. Is simply the product. So the efficiency of turbine gen is simply the product of the efficiency of the turbine times the generator separately. Luckily, we have the efficiency of the turbine, so it's just a matter of rearranging this formula. We already got the turbine generator combined efficiency, so all we have to do is just isolate the turbine efficiency. So let me just write that down as a whole, and then divide this one by gen. So we have here as point, I'm just going to use the old one, 7595 divided by the efficiency of the generator, which is at 0.95. And this should give us, so 0.7595 divided by 0.95, 0.7995 or 0.8. So 0.7995 or roughly 0.8. So it's 80%. Okay. All right. So we are not yet done, and we are left with what's the work shaft? What is the shaft power supplied by the turbine to the generator? Again, recall our. Let's just put it here. So that's A. This is B. So let's just put it B here. Yeah, and then let's just put CD though. All right. I think we can just squeeze it out. No. So for us to determine the work shaft output, remember there's another formula for turbine, and the efficiency for turbine, if you recall, is also equal. The efficiency for turbine is also simply mechanical power output and divided by mechanical power decrease of the fluid. And luckily we have that, so we have this one. And all we have to do na lang is just determine the mechanical power output dito. Okay? So yung mechanical power output, so yung inlet natin dito will be the fluid decrease, or basically the mechanical energy generated by the fluid, and then which in turn the shaft here, which turns the shaft connecting to the generator. So we need to determine the work output there. So that's our mechanical power output. So that's our unknown. So we just put the formula here. It's gonna be work shaft out divided by the absolute value of in mechanical energy of fluid. Luckily, we already have this, and we determined that to be 2451.5 kilojoules per second. So, and we already know the efficiency of our turbine here. So all we have to do is just isolate the mechanical power output. So basically, that's the work shaft, the shaft power output, and we will have this equation. Shaft out is equals to times the mech fluid, and that is simply equal to let's just use 0.7995 times 2451.5, which will give you 0.7995 times by 1.5, which will give you 1959.97 kilowatts, or simply 1960 kilowatts. There we go. So, nagkasya tayo. There we go. All right. So again, just remember that to get the efficiency, it's always gonna be Paul. You're gonna get the efficiency of a pump, motor, or turbine. Always check what's your output and your input, and so that you won't be memorizing a lot of you won't be memorizing a lot of formulas dito. Just remember that for a pump, it's usually mechanical power input and mechanical power, basically the mechanical power increase of the fluid, and then the mechanical power input. And then for turbine naman, it's gonna be mechanical power output divided by mechanical power decrease of the fluid. All right. Essentially, it's electrical power in and mechanical power out. For turbine naman, it's more of mechanical power in and then electrical power out, as observed here sa turbine and generator efficiency. Okay, and for pump motor efficiency, that's simply the again mechanical power out and electrical power in divided by electrical power in. All right. Okay, so finally we go to Bernoulli and energy equation. So I know there's a lot of formula there, but technically there's one formula that you should already know, is that the Bernoulli equation on two different points, mainly in energy form, which is technically this format. So that's going to be P equals to density G plus V squared over 2G plus A or H, which is constant. And for steady flow along a streamline and in two different points, we could rewrite that equation to represent the 2 points as P1 over density over G plus so this is in head form. Basically, we're writing this in head form, as you can see here. And then this is going to be equal to P1 squared 2G plus Z2. Z1 first, and then here's going to be P2G plus V2 squared 2G. Okay, it's the dynamic pressure, the static, what do you call that in head? Let me just recall that lang. It's gonna be, yeah, this is gonna be the pressure head. This is gonna be the velocity head or dynamic head, and this is gonna be the elevation. And then here is the Z2 plus Z2. So yeah, that's one of the forms of the Bernoulli equation. So before again diving, we're just recalling the equation here. So let's start now with the problem. So here we have sample problem 4. Since we have a figure drawn here, something that you've done as a child, where you pinch with your thumb the outlet, the hose outlet, and making a gush and making a thin jet of high-speed water to emerge. So here we have a water is flowing from a garden hose, and a child places his thumb to cover most of the hose, and then the hose outlet causing a thin jet of high-speed water, splash. And the pressure in the hose just upstream of his thumb is 400 kilopascals. So just here is 400 kilopascals. So that will be our P1. And if the hose is held upward, we're being asked what is the maximum height that the jet could achieve. Interesting. So we're point 1 and point 2 at the maximum height. So we're being asked at the height. With just below the thumb, our reference points to 0, so that we know our distance there. So it's important to establish our reference point there first. Okay. So there's a little bit of kinematics here, and we have several clues. We know that at maximum height, we know that our v2, our final velocity, is probably 0 then. We know that the acceleration due to gravity is assumed to be 9.8 meters per second squared. We're talking about water here, so we know that density is gonna be 1,000 yeah, kilogram per meter cube. And we know very well also that at point 1, we can assume at point 1, the velocity inside the hose is relatively low, and we take the elevation just below the hose, just like here. So we can assume that V1 here is going to be 0. Okay, since we're starting our reference points from here, since this is the part where it started to increase the velocity. And then somewhere along the way here, V2 starts to decrease further, goes down further. Okay, so hence you start your velocity 1 at 0, increases speed somewhere in the middle, and then decreases it somewhere at the maximum height. So the same way from your statics, from your mechanics dynamics class before. Okay, and we can also assume that for P2, since it's gonna be released in the air, it's gonna be atmospheric. Okay. P2 is gonna be atmospheric. Right. So we have P1 here at 400 kilopascal. It makes sense because the increase in pressure here, and if you're gonna know your equation mo for the pressure, there's a decrease in velocity then. So almost 0 yung velocity mo. Okay. So as for our solution, so I already wrote our equation na gagamitin. So this is our recall. This is the equation in pressure form and head form. So this, sorry, and then this is the head form at 2 different locations, point 1 and point 2. So let's now try to apply our assumptions here, our known values here, and try to determine what's the maximum height. Okay, so what will happen now here is our P1. Let me just put it here now. Let's just in fact, let's just put everything here. Just delete that. So we're just gonna put everything here. Quite enough space, and then what will happen dito? So we know that P1 is gonna be potentially 0 dito. P2 is gonna be 0 at maximum height. We know also Z1 as 0 since that will be our reference point, so it's 0, leaving Z2, which is our unknown, which is the maximum height. So this will be our, let's just label this as Z max. Okay, and then what else would we know that P1 we have pressure 1 at 400 kilopascal. We also have pressure 2, so let's just change this to P atmospheric. Okay, and now we can rearrange our equation by eliminating the zeros. So we have P1 here, which is over density times acceleration due to gravity equals P atmospheric, or P2, divided by density times G, and then plus Z2. Okay. So this is a matter of just rearranging the line equation to determine what is our maximum height. Although, let's just label it as Z max now. Yeah. Z max, so that we are consistent. So rearranging the equation will give you P1 minus P atmospheric, because you have the same denominator anyway, divided by the product of density and acceleration due to gravity. And take note, if you recall what this formula is, technically this is gauge pressure. So P1 kasi is your, so to speak, absolute, is your absolute pressure, diba? So this will be your gauge. Yeah, o nga pala, no? So again, 400 is not our P1 dito. Okay, but 400 here essentially is your gauge pressure, P1 gauge, so to speak. Okay, So this will be your gauge. So that this one is your gauge P, yeah, PG gauge, yeah. So that will be your 400 kPa divided by 1000 times 9.8066 meters per second squared. And this will build into just Pascal. So we have to multiply this by 1000 Newton per meter squared divided by 1 kPa, and then 1 kilogram meters per second squared over 1 Newton. Yeah, there we go. This would cancel out. And what we'll be left with is meters. So the answer here is gonna be 400 divided by 1000. There's 8.8066 times 1000. So that'll be 40.79 on my end. 40.789 meters, or roughly 40.8 meters. Okay, so again, the pressure in the hose just upstream of this thumb is 400 kilopascal. So apparently that is that's not P1. If the hose is held upward, what is the maximum height? So basically, when you do this equation, P1 minus P atmospheric, that's your gauge pressure there, okay? Or your P1 gauge. So I'll just put that here. There we go. All right. Next up is the sort of a derivation for Torricelli's equation. We're going to do that with a sample problem instead of just giving you the formula. All right, so now we have sample problem number 5. This is where we get to expand more on how to determine Torricelli's equation. Okay, so for here we have a large tank open to the atmosphere, and which is filled with water at a height of 5 meters. Okay, so this one's open, by the way. So 5 meters from the outlet tap shown below here. So that'll be our frame of reference. A tap near the bottom of the tank is now open, and the water flows out from smooth and round outlet. Determine the maximum water velocity at the outlet. Okay, so so the requirement here is that we need to find velocity at point 2, so V2. So that's gonna be in meters per second. Okay, what are we given? So we know that it says that the large tank of the atmosphere is open. Okay, so open to the atmosphere, meaning our P1 here is basically atmospheric. All right. The same way also with our P2, since the opening here is also exposed to the atmosphere, so this one is atmospheric. So hence P1 is P2. Okay. What else? So we're given an elevation Z1 at 5 meters, and Z2, since it's going down, this is gonna be Z2 is 0. Okay. So let's write now our Bernoulli equation. So several assumptions mula dito, no? The flow is incompressible. Okay, that's good. And and rotation except very close to the walls. The water drains slowly enough that the flow can be approximated as steady. So steady, so meaning this one is very streamlined lang siya, steady flow and streamlined, and it doesn't really cause much, turbulence. Okay, and there are irreversible losses that's gonna be experiencing in that tap is gonna be neglected muna for the meantime dito. Okay, since yun yung pinaka-requirements ng Bernoulli equation, Bernoulli energy equations natin. Okay? We can also assume that the water is draining slow enough that our V1 is practically zero. Okay. And P1 and P2 is going to be exposed to atmosphere. So we write now our equation in head form. That's one of the forms that we can use. So that's P1 over the product na density and acceleration due to gravity. And again, density here would be, water, but that's okay. And then our velocity head is V1 squared over 2g plus A1 equals to P2 and then plus P2 squared 2g plus Z2. Okay. So several things kaagad na magka-cancel out. For one, since exposed to atmospheric pressure yung pressure 1 natin and then yung outlet 2, pressure 2, so 0. V1 is practically 0 since it's gonna be a steady flow and gonna be drained slowly lang at the start. At the start, 0 naman talaga yung velocity. So, 0, 0, and 0. Our Z2 is 0. Since yan yung reference point natin. Here lang meron tayong 5 meters. Okay, so that's 0. And rearranging the equation, we're only left with this formula. Z1 is equals to V2 squared over 2G. And guess what? Yun yung kailangan natin. So, actually, lagyan natin siya dito. And if we arrange that further, we can now find V2 here. V2 is gonna be equals to square root of 2j z1, which technically this one is this is essentially the Torricelli's equation. Torricelli equation. Okay, and all we have to do na lang is just substitute the known values that we have. So here we have square root of 2 times 9.8066 meters per second squared times Z1 at 5 meters. So the ending here will be meters per second. So our final answer would be square root of 2 times 9.8066. 9.66 times 5. That'll be 9.9. That'll be 9.903 meters per second. So that's one of, and Torricelli's equation is very useful for finding the velocity at the endpoint of an orifice. So it could be at this level, it also could be at this level then, okay? Okay, so here naman we have another sample of Bernoulli energy equation. Here we have to siphon a gasoline from a car and then lipat natin sa gas can natin. So let's read the problem. So during a trip to the beach, so it has this is 5 atmospheric. We have the atmospheric at 1 atm or equivalent to 101.325 kilopascals. Okay, and a car runs out of gasoline and it becomes necessary to siphon the gas out of the car for Good Samaritan. Hindi pa sinabi, pero you're practically seen as stealing naman din eh. So the siphon is a small diameter hose, and to start the siphon, it is necessary to insert one siphon end in the full gas tank and fill the hose with gasoline via suction, and place the other end in a gas can below the level of the gas tank. So the difference between the 0.1 at the free surface gasoline, so this one, and 0.2 at the outlet of the tube is gonna be 0.75 meters below 0.1. So there we go. And 0.3 is located 2 meters above 0.1. So 2 meters above 0.1. The siphon diameter, this one is 5 millimeter, and the frictional losses in the siphon are to be disregarded. We are to determine A, the minimum time to withdraw 4 liters of gasoline from the tank to the can, and B, the pressure at 0.3. We are given also the density of gasoline at 750 kilogram per meter cube. Okay. Sige. So for here, we can also, let's start first with the required. So we're here to find the minimum time. So we need delta time T, okay, to fill in 4 liters. Okay, let's just rewrite that. So we need delta time, this for A, at 4 liters, to fill in 4 liters, and B, the pressure at 0.3. So this is gonna be in kPa. Okay. So we're given the density of gasoline at 750 kilogram per meter cube. What else? What can we observe pa, no? So we're given atmospheric pressure, and both 0.1 and 0.2 are exposed to atmospheric pressure. So that's going to be atm. The velocity at 0.1 is relatively, it's going to start at 0. And what else? We have elevation difference between Z1 and Z2, which is gonna be 0.75. No, actually, Z1 lang pala. Z1 is our 0.75 and Z2 is our reference baseline at 0 meters. So from here, we can actually build na yung Bernoulli equation natin. So again, in head form, P1 G plus V plus 2 squared 2G plus Z1 plus V2 G plus V2 squared 2G plus Z2. Let's cancel up. So we know this is atmospheric, so pwede siya mag-cancel out dyan. And then what else? This one is relative to 0. So cancel out. And then what else? Our Z2 is gonna be 0, which would leaving us with this equation. Z1 is equals to V2 squared 2G. Familiar. It's kind of like our Torricelli's equation. And then from here, we can now determine the velocity, which is simply square root of 2J Z1. So this is simply 2 times 9.8066 times C1 of 0.75. Our V2 here is simply 2 times 9.8066 times 0.75. Square this one is gonna be 3. I got it at 3.8353 meters per second. That's okay. So far, so good. But we're not yet done. We need to determine yung time. Remember, one of the crucial things given also here is we're also given a diameter. If we're given the diameter of the siphon, which is at which is at 5 millimeter pala. Okay, 5 millimeter. And luckily, if you recall yung formula natin, volume flow rate is also equal to the fluid velocity times the area, and all we have to do here is get the volume flow rate. So we simply substitute our V2 here, 3.8353 meters per second times pi over 4, t squared, so 5 millimeter, which is essentially 5 divided by 1000. So there we go. That's 0.05 squared, and the volume flow rate is equals to 3.85, okay, 3.8353 times pi over 4 times 0.005 squared. So that's gonna be in meter cube. Wait lang. Meter squared. So this is gonna be 0.000, too many zeros, 7.530 meter cube per second, or simply multiply that by 1000. Liters times 1000. And that will give you 0.0753 liters per second. Luckily, we're being asked the minimum time to withdraw 4 liters of gasoline. So we already know our volume. I'm not sure how to properly volume is 4 liters. So to get time t, that will be volume over volume flow rate, which is simply 4 liters divided by 0.0753 liters per second. And that would give you 4 divided by, that would give you about 53.12 seconds. So yeah, so that it will take you about 53 or almost a minute to get 4 liters of gasoline. So let's just box that in. Yeah. For letter B, we're here to determine the pressure at point 3. All right, so let's add another slide. So for point 3, so for letter B, so finding P3 kPa. What we can do is we can reference it from point 2 to point 3. So we have our equation just like so: P2 over G, density times acceleration due to gravity, velocity 2 squared over 2G plus Z2 is equals to P3 G plus P3 squared over 2G plus Z3. Okay, so the thing is, with V2 is equals to V3 due to conservation of mass, they have the same velocity here. Our Z2 here is still 0. Our Z3 here is 2.75. And our pressure here, and that's what we're trying to determine. Luckily, we know what P2 is. This one is atmospheric, so we have our values dito. And we're already given that. So, rearranging equations dito. So, we have Z2 here, 0. This one's going to cancel out. And we have Z3. And P2 here is simply P atmospheric, which is already provided. So our final equation here is P atmospheric G equals to P3G and over density times G plus Z3. Now solving for P3, isolating it, P3 is now P atmospheric minus rho times acceleration to gravity and Z3, which kind of resembles your pressure head. And we're back in fluid statics, right? Right? So all we have to do now is just simply substitute the equation known equation. So we are given with atmospheric condition 101.3, which is already provided here. That's kilopascal. Minus density, we are given density at 750 kilogram per meter cube. I'm going to multiply 9.8066 here, meters per second squared. We're going to multiply Z3 as 2.75 meters. Yeah, and then we're just going to convert that Newton into kilonewton so that we have kilonewton per meter squared. So it's going to be times 1 kilonewton divided by 1,000 newtons. Okay. So let's just cancel units. So this one is going to be a Newton. This is going to be meter squared. Just cancel. So kilonewton per meter squared. So your P3 now, just put it here. Actually, pangit. Let's just arrange this. So solving the equation here. Your P3 is now 750 minus 9.8066 175 divided by 1,000. 101.3 minus, so P3 is around 81.0739 kPa or 81.07 kPa. Yeah. Okay. There we go. Okay. All right, for one final sample problem for Bernoulli energy here, we have here a piezometer and a pipette tube, and they're tapped into a horizontal water pipe. So horizontal water pipe. So this is your pipette tube, your piezometer and your pipette tube, and shown in the figure below. And to measure, it is to measure the static and stagnation pressure, or static and dynamic pressure. Stagnation meaning static plus dynamic pressures, respectively, for the indicated column heights. So to measure the static and stagnation pressures. So for indicated water column heights, determine the velocity at the center of the pipe. So they want to determine V1 here, basically. So actually V1 and V2 is practically the same rin naman. So it's one steady flow rin naman, one steady flow and incompressible. And points 1 and 2 are close enough together that any irreversible energy losses between the two are negligible. Okay. So what do we do here? Okay, so first things first, we just want to find. We're gonna find v1 basically. It's meters per second. So what we do here, we take points 1 and 2 along the streamline and the center line, with point 1 directly under the piezometer, and then point 2 at the tip of the pilot tube. And from here, we can actually get now the pressure, the gauge pressures P1 and P2. So you can actually get P1 here and P2. That's our gauge pressure, by the way. So solution, we'll set that up muna. Hopefully you still remember your fluid statics. So at point 1, you want to know the gauge pressure here. That simply is the rho times acceleration to gravity, and that's H1 plus H2. P2, on the other hand, is simply H1 plus H2 plus H3. Okay, so far so good. Next up is that, what else do we notice here? We notice that they are of the same elevation, so Z1 is equals to Z2. So let's just put that observation. The Z1 is equals to Z2. Let's just put also the V1 equals to V2, so that's fine. Oh, my bad. No, di pala. And at this stagnation point, basically V2 is, point 2 is a stagnation point. So meaning V2 would be 0. Okay, leaving us with only V1. So we can now apply our Bernoulli equation here, which if we are going to write it in head form, how we solve this? C2. Okay, and then we just cancel the one, so it's going to be 0. So here is 0. Z1, Z2, since they're the same elevation. Yeah, that's pretty much it. And then we can now rewrite the equation something like this. Okay. And we can now substitute our equation here. So that will give us P2 is simply times H1 plus H2 plus H3 minus H1 plus H2. Okay. This will cancel out since H1 minus H1, so this one's gonna minus out. This is gonna cancel out, leaving you only with H3. So the new equation here would be Vi squared 2G is equals to H3. And to determine the velocity, isolating velocity 1, simply 2G H3. So this resembles our Torricelli's equation. And all we have to do now is substitute our known values, 9.8066 meters per second squared. H3 is 0.12 meters. And V1 is 2 times 9.8066 times 0.12, and then we get the square root that, square root of that. That will be 1 point, oops, that will be 1.5341 meters per second, and then box that answer. So if you notice, to get V1, we simply get the difference to determine the flow because all we need pala is to measure the height of the excess fluid here. So let's just highlight that as purple. There you go. In the pito tube and compare that to the piezometer. So in this case, it's H3 is 12 centimeters. And we get applied to Cherry's equation dito, which is, if you recall, is 2GH or Z. Okay. Okay. So that's it. And on our next lesson, we'll proceed with more live board problems.